Welcome to Chapter 3E. In this segment, we'll explore the Peptide Details tab, where you can drill down into individual peptides, view supporting MS2 and DIA data, and examine key peptide properties in detail. Let's get started.
All right. One of the important tabs that you may want to use from time to time is the Peptide Detail tab. And that tab can only be shown once you've clicked on a peptide in the peptides table, or if you clicked on a peptide in one of these views. All of these dots and all of these lines are clickable. So if you select the peptide from the peptide table or the other views, you will get a Peptide Details tab shown here. And this tab will show you the following data. On the top, you'll have your replicates for the selected state and labeling. In this case, I have a time point labeling, a time point selected, as well as a state. The state in this case is the target, and in this time point slash state, I have 3 replicates for this peptide. And you can select each replicate from this table here. The MS1 data for this peptide is shown in the top right. This is the precursor data that you would see in a normal conventional experiment. The XIC of the peptide is in the top left. The XIC of all the fragments in DIA space is just below the peptide precursor XIC. You can see in some scenarios how nicely the peptide XIC aligns with each of the fragment XICs. This is actually very useful in the software. It helps the software to localize the peptide in time by basically creating correlations between each of these fragment traces as well as the precursor. So in order to localize a peptide in time, it'll extract the peptide XIC, it'll extract all the fragment XICs, and then it'll look for the area of maximal correlation in a peak where it has high correlation to set the actual retention time for this peptide. Without DIA data, this would have to be done just relying on fitting this distribution in MS1 data only, which is doable, but it's easier when MS2 data is present. The bottom part of this view is going to be the fragment duration model on the left and the actual MS2 data on the right. I'll start with the MS2 data. The MS2 data will show you all of the fragments that were detectable and measurable in this peptide, in this replicate. And by default, it'll only show you the part of the spectrum that is relevant for this peptide. Remember, we're doing DIA here, so there could be multiple peptides fragmenting together. And so we have this checkbox on the MS2 spectrum that says show only fragment ranges. If I disable that, you'll see that additional data shows up at the bottom here that's not labeled. That is what your actual MS2 data for this DIA window looks like. But just to kind of keep things clean, this option just shows you the fragments that belong to this peptide only. The fragment labels are scrollable, so you can just hover over a fragment label to see the underlying data without having to zoom from the x-axis, which you can do, but it's sometimes just easier to just take a quick peek on each fragment label to see the underlying data and whether it's clean or not clean. The exact same data is presented here on the left side, but it's just now plotted on a deuteration versus the relative size of each fragment plot. And what this plot is supposed to show you is that it is the linear trend that we expect for each fragment deuteration measurement to fall on a linear trend compared to the peptide precursor deuteration. That is because with full scrambling, all of the hydrogens on the peptide are randomly distributed, so that anytime we cut away a fragment of that peptide population, that population of fragment will on average have the relative deuteration relative to its amount of hydrogens that it's carrying. So a small fragment will carry only a fraction of the total number of hydrogens of that peptide, so it'll have fewer deuterons that can be part of that fragment. Whereas a fragment population that contains more of these scrambling hydrogens then can actually have a higher degree of deuteration. So what this makes is a linear trend that we can fit with a line, and that line will tell us the MS2 derived deuteration for that peptide. The MS2 deuteration for the peptide is also taken into account several measurements, several quality measurements of each fragment, and they are based on the intensity of the fragment, the fit of a deuteration model, as well as the relative length for each fragment and how many peaks we're matching for that fragment. So altogether, those will create the weight of each fragment, and these weights are then used in the fitting of this linear trend to this data set. So what does this mean, right? Well, this linear trend of fragments will easily give us an MS2 measure deuteration that can actually be very, very useful. Let's say in cases where the peptide MS1 data would be completely overlapped and compromised, then the deuteration for this peptide can be derived from its MS2 data. And I will show you an example shortly. Here's an example of an overlapped peptide where the DIA data can actually give us its true deuteration even though its MS1 signal is completely compromised. So our target peptide is this monoisotopic peak here starting at 854.43. And as you can see, there's another peptide that is charge 3. Our target peptide is charge 2. The charge 3 overlapping peptide is going to create issues for the third peak, for the fifth peak of our target peptide, and for the seventh peak of our target peptide. If these peaks were included in the centroiding calculation for this peptide deuteration measurement, that measurement would be overestimated. In this case, the software was able to deconvolve these two peptide signals, and you can see it's fitting deuteration model to the peaks that are not overlapped. But even if it wasn't able to do that, even if these peaks were perfectly overlapped completely throughout the entire peptide, throughout the entire MS1 spectrum, it wouldn't matter because the peptide deuteration is now still measurable in MS2 space. You can see here, at least I have a Y11 ion that is very nice, high intensity, and a clean fragment that reports the peptide deuteration exactly. Same with the B9, the Y8, the Y9. Not all of the fragments are going to be useful. For example, here I have a fragment that's overlapped, but I don't need every fragment to be clean. I only need the high intensity, I only need a few high intensity clean fragments to get the peptide deuteration measurement only from the MS2 data. So we can absolutely rescue peptides that would otherwise be completely deleted in a conventional MS1 only analysis just because they are overlapped. When you select a peptide from the peptides table or from any view, you will also see this properties panel on the right side of the screen. This will contain certain information about the peptide like charge, the number of exchangeable amide hydrogens that it has, its monoisotopic mass, as well as the deuteration measurements for that peptide. And they are split into 3 measurement groups. So the MS1 deuteration are the first 3, then the MS2 are the next 3, and the final chosen deuteration for this peptide are the final 3. Again, the final deuteration is either the MS1 or the MS2 deuteration based on which one presents the lowest amount of error across your replicates. So in this case, it's the MS1 deuteration that has been chosen for this peptide. So just going from the top down, for each of these groups of deuteration values, you have your normal difference of centroid deuteration measured in Daltons, your MS1 percent deuteration, or just the percent deuteration, and then followed by the corrected percent deuteration for this peptide. If this peptide was an EX1 peptide, you would have information in this EX1 deuteration expandable option here. If it was EX1, it'll show you the actual deuteration for the slow and the fast populations for this peptide, as well as the population sizes as well, right here in this section here. I'll close that. The quality fit of the peptide goes from 0 to 1. 1 means it's a very high quality fit to the observed data. So that is this black line fitting the marked peaks that are labeled in gray. If this fit is really good, it'll be very close to 1. If this fit is very poor, it'll be close to 0. The other controls that are available on this properties panel are to turn certain views off and on. So for example, if I turn off the show deuteration ranges, you'll see that these gray bars disappear. These gray bars just mark where the peptide peaks are expected to exist. for this particular peptide once it's deuterated. And then the fitted deuteration, which will be the black line fitting the peaks here. This is the model that the software has chosen to fit the observed data to represent the peptide deuteration model. That can be shown and toggled off and on, as well as the non-deuterated version of the peptide here in red. So this would be how the peptide would look like if it had no deuteration, no deuterons in its sequence. It's just a normal theoretical isotopic abundance that you'd find in nature for this peptide. Note that the height of this red distribution is scaled down just to match the height of the black distribution, just because it's easier to see. But in reality, this red distribution would be a little higher because in reality it's the same amount of signal but spread out throughout more isotopes later when it deuterates. So this is just for viewing. Finally, the processing options presented here are this retention time start, retention time stop. These are modifiable, so if you disagree with the software range selection for this peptide, you can change it. So for example, here I changed it from 11.74 to 11.64, and when I hit reprocess, it'll re-extract that data in that region. Another way to do this exact same thing is to just simply click and drag on the XIC itself. This will integrate that particular range and re-extract the MS1 and MS2 data and do all the calculations once again. The EX1 flag here is for whether your peptide is bimodal or not. In this case, it's definitely not, as you can see here. But if you do enable this, it'll force two binomial distributions to fit this data as a bimodal. But in this case, the peptide is definitely EX2, so I will not turn that on. The used in calculation flag is not used if you're using DIA data. This is for manual validating of completely conventional MS1 only data. When you're using MS2 data, this option doesn't do anything because the software will make an automatic decision on whether to use the MS1 or MS2 deuteration, whichever one is more reliable.
That covers the Peptide Details tab and how to dive deeper into your peptide data. Next, in Chapter 3F, we'll explore the kinetics view, where you can visualize and analyze the rate of hydrogen-deuterium exchange in proteins. Let's move forward.